right, we're going to be doing a little bit out of your notes on limiting reactants. This is kind of the key point of doing that expanded mole. So this is the problem that's in your notes. And the limiting reactant, it's like that snowflake worksheet and it's like the breakfast worksheet. When you run out of something, that limits what your product's going to be. So if you only have 5, of these things, that's as many as you can get in the product. So if you need to have 2 eggs for your pancakes or your whatever, you only have 1 egg, you're limiting how many pancakes you can have. And that's going to result in your product. So when you do these problems, we still have to have a balanced equation. We got to know what kind of equations we're working with. We got to be able to write our formulas out, do all those things. So I'm going to do the 2 that are in your notes and kind of walk through them with you. And then you can apply those to those worksheets that you got last Friday. Okay? Those of you that were working on them can go back and look and see how you're doing and then do some of those other problems that you didn't do. And then we'll talk about percent composition. We'll do those when I do some of the worksheet problems tomorrow from your 11.3 practice problems. So the first one that I did was how much jump down too far. How much sulfuric acid, let's get the right one up here. This is what we're going to start with. How much sulfuric acid can be prepared from 5 moles of sulfur dioxide, 1 mole of oxygen, and unlimited H2O. I want you to make special note that when you see this in a problem, either the word unlimited or excess, you know that, hey, I don't have to probably worry about that reactant or even that product if I'm figuring out what is my limiting reactant. So unlimited and excess are they're good terms to know because they're going to help you not do a bunch of extra work. So in this problem, we have the balanced equation, which I gave you. We're going to now look at the 2 products that we need to worry about. We got sulfur dioxide and oxygen. This one's unlimited, so we're not worried about H2O. So we had to set up 2 problems. And because this is a mole comparison, we can just compare moles to moles. So we have 5.0 moles of, and we have 1.0 moles of oxygen, and we want to turn those into our sulfuric acid. So we got to know what is our comparison between those 2. So on this first conversion, I look at moles of sulfur dioxide, which is 2 moles. SO2 is 2 moles of H2SO4. Those cancel out. I can do my second equation right underneath it. I have 1 mole oxygen to 2 moles H2SO4. Those cancel out. And then I do my work. Okay? So this one comes out to be 5.0 moles H2SO4. And this one comes out to be 2.0 moles of get my eraser here. H2SO4 also, because that's what we're looking for in our products. I canceled out here and then do it. So, what is the right answer? This is another thing where when you're first exposed to this, we always go with, well, whatever gives us the most is what we want for our product. But remember, this is limiting reactants. So, the right answer is the one that always gives you the lowest value. So, you would want to circle this whole bottom one, which I did in your notes. That's what we can get. Oxygen is going to limit this reaction. So in this example, giving these values, that's the most sulfuric acid we can get in terms of moles of sulfuric acid. Okay? So then we had to amp it up on the next one, which was that first sheet you saw up here. And that's with the barium nitrate and the sodium phosphate. Now here, I give you the problem. I say a solution containing 3.50 grams of sodium phosphate is mixed with 6.40 grams of barium nitrate. How many grams of barium phosphate can be made? And I didn't give you the equation. You had to actually write out the equation. This is a double replacement reaction. Here's my two reactants, and I gave you one of the products, the one that we actually want. Ba3, PO4, 2. But we also need to have the other product because we have to have the balanced equation. So if we know it's a double replacement reaction, then I know that the sodium has to go to the nitrate. And then I got to go back and, hey, well, what are my right formulas for this? Okay, is that the right symbols for everything there? And I look at sodium, barium, that's right. And sodium nitrate happens to be right, and then we have to balance it. So when we balance this, and I'm just going to do it quick for time's sake, we get 2, 3, and then a 6. And that gives us our balanced equation. All right? So we have to, again, set up two problems. I have two reactants to get this product. We are not worried about this one at all. It doesn't matter. We don't need to solve for it. It's not asked. So we set up these problems just like you see them in your notes. So I take my 3.50 grams Na3PO4, and we need to convert that into barium phosphate. And to do that, it's going to take us 3 conversions. First one is we need to know what is the molar mass of sodium phosphate. So we know that 1 mole of sodium phosphate is 164 grams of sodium phosphate. Okay. Put my 3 there, get my in the right spot. I can then do my mole conversion. Okay, so what are my relationships here? I have 2 moles of sodium phosphate to 1 mole of barium phosphate. Okay, that's all good. Now, a lot of times, if that's all it's asking for a limiting reactant, we may be able to stop there. But in this case, I asked how many grams do we have to get? So I do have to have that third step, which means 1 mole of barium phosphate weighs how much? And this one, we got a lot to add up. We got 3 bariums, 2 phosphates, and 8 oxygens. And this guy comes out to be 602 grams of barium phosphate. Okay? And we cancel those things out. We plug in our numbers. We have 3 sig figs. And in this case, we come out as 6.42 grams of Ba3PO4. And I'm running out of room on my little tiny board here. Okay, so that's the first one. I got to do my second one, barium nitrate, into the same thing. Now, I have some work that I get to use again, which is nice. So we take a look at that. We have 6.40 grams of barium nitrate. And we do the same thing. First, we convert it into its moles. 1 mole barium nitrate is how many grams? Well, we calculate that up. This comes out to be 602. 261 grams. Okay. We then look at our mole conversion. Barium nitrate to barium phosphate. So barium phosphate is what we want. So that's 1 mole of barium phosphate is equal to 3 moles from our balanced equation of barium nitrate. Those cancel out. Should cancel those out too. Grams are gone down to moles. But I want to have grams of barium phosphate. So we use the same thing again, 602 grams of barium phosphate is equal to 1 mole of barium phosphate. Those cancel out. And when we get our answer here, we get an answer of 4.92 grams of Ba3PO4 2. Okay? And this is our limiting reactant. So the barium nitrate, when I go to it, says, so what is my limiting reactant? I say limiting reactant is BaNO3 and that's a 3 there. Sorry. BA, make sure I write this. I know there's no 2 there. I don't know. I got a 2 on that. Okay, get rid of those. So it's limiting reactant is barium nitrate. That's it. Okay, that's what you're doing on those problems. Yes, you need to set things up twice. Usually not 3 times, but there's usually 2 reactants or maybe even 2 products. Another thing that you may run into, and you're like, oh, what am I supposed to do? It doesn't ask you. It says you're reacting these 2. Which one limits this reaction? If it doesn't give you a choice on your products, you can pick whichever one you want to. And I always tell my students, always pick the one that's easiest. So if water is one of your products, pick water because we know the weight of water is 18 grams for every mole. So if you pick the easier one, it's easy. Carbon dioxide, 44 grams per mole. If it doesn't ask you to do a specific one, pick your own. So don't panic because it doesn't tell you which one to pick. Just pick one out because you guys know how to do the math part. The concept part is this. If you can do this part, you can do anything in chemistry. And in chemistry, this is the big deal. Those of you that want to go into engineering. The limiting reactant is where you're going to save your company money. If you're spending money on certain reactants, and some reactants cost hundreds of thousands of dollars for just a tiny amount. And if you're making a product and you're using more than you need to of that $100,000, the new chemist comes along and says, hey, we can use 5 grams instead of 20 grams. That guy's going to get your job. And that's how it works. So you got to know how to do the math. The math is super important. All this dimensional analysis stuff is super important. And it goes on in all your science classes after this. Okay? So keep working on this. I'll have another one. I'll do some examples from our 11.3 practice problems. Work on your reviews. Today you're going to get some quizzes for my juniors that are left in class. And those will be due next week. So I'll talk to you tomorrow on another little video. Do some more examples and even do some percent compositions, percent yields. Okay? So talk to you then.